Let's talk a bit about tuning your neural networks. This is not stuff that is typically taught, but I'm going to try to convey it as best as I can. So let's talk about learning rate first of all. What do we mean by learning rate? Well, you need to understand how these neural networks are trained. They're using a technique called gradient descent or something similar to gradient descent. There's various different flavors of it out there. The basic idea is that we start at some random point of weights in our neural network, and we just sample different solutions, different sets of weights, trying to minimize some cost function that we define over several epochs. So those are the key words there. We have many epochs, iterations over which we train. At each epoch, we try a different set of weights on our neural network, trying to minimize some cost function, which might be the overall accuracy of how well it makes predictions on our validation set. So we need to have some sort of rhyme and reason as to how we make those samples of different solutions, different weights, if you will. If we were to boil this down into sort of a two-dimensional graph, maybe it would look something like this, where we're just sampling different points here along a curve of solutions. And we're trying to find the one that minimizes the cost function. So that's the y-axis here. So what we're trying to find is the lowest point on this graph. And we're trying to get there by sampling it at different points and learning from each previous sample. That's what gradient descent is all about. So the learning rate is all about how far apart those samples are. So you see here, we might have started up here, and our learning rate said, okay, I'm going to try another point here, and I'm going to try again here, so on and so forth, until I finally find the lowest point along this curve and call that my best solution. So, not too hard to understand the effect of learning rate on your training, right? If you have too high of a learning rate, you might overshoot that solution entirely. So, imagine my learning rate was huge and I went straight from here to here. I might miss that bottom point there entirely if my learning rate were too high. But you can see that if my learning rate is too small, I'm going to be sampling a whole lot of different points here, and it's going to take a lot of epochs, a lot of steps to actually find that optimal solution. So too high of a learning rate might mean that I overshoot the correct solution entirely, but too small of a learning rate will mean that my training might take longer than it needs to. Now, learning rate is an example of what we call hyperparameters. It's one of the knobs and dials that you use while training your deep learning model that can affect its end result. And oftentimes, these hyperparameters can have just as much influence on the quality of your model as the topology of the model, the feature engineering you've done, and everything else. So it's just another piece of the puzzle here that you need to arrive at experimentally. In addition to learning rate, another important hyperparameter is the batch size. And this is how many training samples are used within each epoch. Now, hammer this into your heads, guys, because it's kind of counterintuitive. You would think that a large batch size would be a good thing, right? The more data, the better. But no, that's not how it ends up working. It turns out that if you have a small batch size, it has a better ability to work its way out of what we call local minima. So in this example here, you can see that we have a minima here, sort of a dip in the graph here, where we have a pretty good, nice low loss function value here. What we're trying to optimize for is pretty good here. But there's a risk during gradient descent that we get stuck in that local minima, when in fact the better solution is over here somewhere. So we want to make sure that during the process of gradient descent, we have some ability to wiggle our way out of this thing and find that better solution. It turns out that smaller batch sizes can do that more effectively than larger ones. So a small batch size can wiggle its way out of these local minima, but a large batch size might end up getting stuck in there, like basically weighing it down, if you will. So batch sizes that are too large can end up getting stuck in the wrong solution. And what's even weirder is that because you will usually randomly shuffle your data at the beginning of each training epoch, this can end up manifesting itself as getting very inconsistent results from run to run. So if my batch size is just a little bit too big, maybe sometimes I'll get stuck in this minima and sometimes I won't, and I'll see that in the end results is seeing that from run to run, sometimes I'll get that answer and sometimes I'll get that answer, right? So hammer this into your head, guys. Is smaller batch sizes tend to not get stuck in local minima, but large batch sizes can converge on the wrong solution at random. A large learning rate can end up overshooting the correct solution, but small learning rates can increase the training time. So remember this, write it down, important stuff. And it's an example of things that most people just learn the hard way through experience, but I'm trying to teach it to you up front here.